All right, let's dive into a topic that might just shake up some of your philosophical assumptions, huh? Today, we're taking a look at evolutionary game theory, EGT for short. It's this fascinating blend of biology, math, and, yep, you guessed it, philosophy. And our guide for this deep dive, the Stanford Encyclopedia of Philosophy's entry on EGT. We're going deep, folks.
What's really cool about EGT is that it's not just about genes and, biological evolution. It's about ideas evolving, behaviors, strategies for navigating social interactions, all that jazz. And this has some pretty big implications for how we think about rationality, cooperation, heck, even the very basis of morality.
Absolutely. I was reading about this puzzle, a real head scratcher, that kind of kickstarted this whole field. It's got elephant seals and this question that really bothered a brilliant geneticist named R.A. Fisher back in the day. You familiar with this one?
Oh, yeah, the elephant seal dilemma, a classic example of how EGT makes you rethink evolution. Fisher was puzzled, right? Because male elephant seals have these huge harems, one alpha male mating with tons of females, so most males. They never even get a chance to reproduce. Seems kind of inefficient from an evolutionary standpoint.
Right. If passing on your genes is the goal, why would that system evolve? It's like a recipe for genetic dead ends.
Well, Fisher figured out the key was to look beyond the individual males, look at their offspring, and even more importantly, their grandchildren. A male who has a bunch of daughters, he has a massive advantage, right? Because each of those daughters is going to have multiple offspring. So even if he doesn't mate directly, his genes are spreading like wildfire through his daughter's success.
So it's not just about your own reproduction. It's about the impact across generations, how your genes make their way through the entire population.
Bingo. And that leads us to this idea of frequency-dependent fitness. What it means is that the success of a trait or behavior, it's not just about its inherent qualities, it's about how common or rare that trait is in the whole population.
And here's where things get interesting for a philosopher, right? This frequency-dependent fitness, it throws a wrench into the traditional focus on individual rationality. Your best strategy might not be the one that seems the most logical on its own. It depends on what everyone else is up to.
Think of it like this. If everyone's aggressive and competitive, a little cooperation can make a big difference. Like the prisoner's dilemma. If you're the only one cooperating, you might get taken advantage of. But if enough people start cooperating, it creates a better situation for everyone.
It's like the tragedy of the commons, right? The logical choice for each person might be to overuse a shared resource. But if everyone does that, the resource gets depleted, everyone loses. Individual rationality leading to collective disaster. EGT really highlights that tension.
And those early insights from Fisher, they laid the groundwork for EGT as a whole field. People like John Maynard Smith, George Price, Robert Axelrod, they took those ideas and applied them to all sorts of things, from animal conflict to cooperation in human societies. It's a broad field.
So we've got this interesting backstory, but how does EGT actually work? It builds on traditional game theory, right? But with an evolutionary twist. What are the core concepts that make it tick?
You're right. It does build on traditional game theory, strategic decision-making when the outcome depends on multiple players. But EGT adds in time, adds in change. It's not just about finding the best move in a static situation. It's about understanding how strategies evolve, driven by natural selection.
Okay, so that's where the evolutionary part comes in. But can you break it down a bit more? What are the main differences between traditional game theory and this evolutionary approach?
In traditional game theory, a big concept is the Nash equilibrium. It's a state where no player can improve their outcome by changing their strategy alone, assuming everyone else sticks to their strategy. It's a point of stability.
So it's like everyone's stuck, but they're all doing the best they can given what their opponents are doing.
Exactly. But the thing is, traditional game theory often assumes that players are perfectly rational, they know everything about the game. That's not always how it works in the real world, especially when we talk about biology or cultural evolution.
That's where EGT steps in, right? It offers a more realistic look at how strategies actually change in a population.
Right. And a key insight of EGT is that what's rational can actually change over time, depending on the dynamics of the game and the strategies everyone else is using.
So it's not about finding one perfect rational strategy. It's about how strategies adapt and evolve in a constantly changing world.
Exactly. And a big concept that captures this whole dynamic aspect is the evolutionarily stable strategy, or ESS. John Maynard Smith and George Price developed this. Think of it this way. An ESS is a strategy that, once it's common in a population, can't be easily invaded or replaced by another strategy.
Okay, I think I'm following. But can you give us a real-world example? It always helps to make things more concrete.
Absolutely. Let's look at the classic hawk-dove game. Imagine a bunch of animals, they're competing for something valuable, like food or territory.
Okay, I'm picturing some birds fighting over the best nesting spots.
Perfect. Now, there are two strategies, hawk and dove. A hawk always fights for the resource. Dove displays, but backs down if challenged.
So, fight or flight. Hawk's all about aggression, dove's more cautious. I'm guessing the hawk strategy wins out.
Might seem that way at first, but here's the EGT twist. A population of all hawks, it's not actually stable in the long run. Why? Because if everyone's always fighting, they get injured, waste energy, might even miss out on the resource entirely.
Ah, I get it. So even though always fight seems like the strongest approach, it can backfire when everyone else is doing the same thing. The costs of conflict start to outweigh the benefits.
Exactly. Now imagine a few doves pop up in this hawk-heavy population. They avoid all that fighting, and sometimes they can even share the resource peacefully if they meet another dove. This means the dove strategy starts to look pretty good, and it starts to increase in the population.
So it's like a balancing act. Too many hawks and doves have the edge. Too many doves, hawks start winning again. This back and forth between strategies.
You got it, and that's a key point. An ESS isn't always one single strategy. Sometimes it's a mix of strategies, like a certain ratio of hawks and doves, or even a cycle where the dominant strategy keeps changing over time. It all depends on the costs and benefits of each strategy within the whole population.
This is really interesting. It's making me rethink how I usually think about rationality. It's not about finding that one best solution, but about understanding how strategies co-evolve and influence each other in a dynamic system.
Precisely. And this is just the beginning when it comes to EGT. We haven't even touched on how these strategies actually change within a population. Do individuals have to be super rational calculators, or is something else going on?
Now that you mention it, that's a question that's been on my mind too. How do we go from individual behaviors to these big evolutionary patterns? It seems like magic, but I'm guessing there's a more scientific explanation.
There is.
Yeah.
And it takes us into this fascinating world of learning models and how they shape the dynamics of cultural evolution. We'll explore that in our next segment. Stay tuned.
Welcome back to our deep dive into evolutionary game theory. We're picking up our exploration of EGT and how it can really shed light on some fundamental questions in philosophy, right?
Yeah, I'm still wrapping my head around everything from our last segment, especially that idea that rationality isn't this fixed thing, you know? It's
Yeah.
constantly changing along with the strategies that are being used in a population.
It's a powerful concept, and it really has some far-reaching implications when you start thinking about it.
You mentioned we'd be diving into learning models and how they help us understand the dynamics of cultural evolution, so let's unpack that a bit. How do we bridge that gap between individual behavior and those big evolutionary patterns we see?
One way to think about it is this. We need a way to connect those micro-level decisions that individuals make to the macro-level trends we observe in populations. It's like the relationship between individual atoms and the behavior of a gas, or the choices individual consumers make and how the stock market fluctuates.
Precisely. And in the realm of EGT, we use learning models to explore how individuals adapt their strategies based on what they're seeing in their environment, and how those individual adaptations can lead to changes at the population level.
Okay, so instead of assuming everyone's perfectly rational and knows everything about the game, we're looking at how people actually learn and change their behavior.
Exactly. And there are a whole bunch of different learning models that EGT researchers use, each with its own set of assumptions and implications, of course.
Can you give us some examples? I'm curious to see how these models work in practice.
Sure, let's start with one of the simplest and most widely used models, replicator dynamics.
I've heard that term before, but I'm not totally sure what it means.
Imagine a population of individuals, each using a different strategy for a particular game. Replicator dynamics assumes that individuals tend to copy the strategies of those who are doing well.
So it's like social learning. You see someone succeeding with a certain approach, you're more likely to try it yourself.
Right. The basic idea is that strategies that lead to higher payoffs are going to spread throughout the population, while those that are less successful will gradually disappear.
Makes sense, but wouldn't that make the population vulnerable to trends or fads that might not be beneficial in the long run?
That's one of the trade-offs with replicator dynamics. It can lead to quick shifts in strategy frequencies, but it's also sensitive to what we call evolutionary dead ends.
So a strategy might become popular for a while, but then lead the population astray if the environment changes or a new, more effective strategy comes along.
Exactly. And replicator dynamics has another limitation. It can only work with the strategies that are already present in the population.
So it can't account for the emergence of totally new strategies or innovations that might disrupt the existing equilibrium.
Right. For that, we need models that allow for more creativity and exploration.
Are there models that address those limitations?
Absolutely. Researchers have developed a bunch of more sophisticated learning models that incorporate things like memory, foresight, and the ability to learn from past mistakes.
So it's like moving from a simple trial and error approach to something more strategic and nuanced.
Exactly. And as we move towards more complex models, we start to see how even boundedly rational individuals can generate some surprisingly sophisticated and adaptive behaviors.
This is all so intriguing, but I can't help but wonder, how do these learning models actually connect to the philosophical questions we're exploring?
That's a great question, and it really gets to the heart of what makes EGT so fascinating for philosophers. These learning models provide a framework for understanding how certain behaviors, norms, and even moral principles might have evolved over time.
So instead of relying on abstract moral reasoning or appealing to innate moral intuitions, we can explore how certain behaviors might have emerged through this dynamic interplay of individual choices and evolutionary pressures.
Exactly. Let's take the example of fairness, a concept that's central to many philosophical debates. Traditional approaches to fairness often focus on finding universal principles or defining what a fair outcome should look like.
But EGT offers a different perspective, doesn't it?
It does. EGT suggests that fairness might not be a fixed concept, but rather something that emerges from social interactions, shaped by the costs and benefits of different strategies in a given environment.
So instead of asking, what is fairness? We can ask, how did behaviors that we now consider fair evolve over time?
Precisely. And EGT models, especially those that incorporate replicator dynamics, can help us explore how different forms of fairness might have emerged and spread through populations.
Can you give us a specific example of how EGT models can illuminate the evolution of fairness?
Imagine a simple game where two individuals have to divide a resource, let's say a pie.
Okay, seems straightforward enough.
Now, traditional game theory might suggest that the most rational outcome is for one individual to take the whole pie for themselves.
Because that maximizes their individual gain.
Exactly. But in real-world interactions, we often see a tendency towards more equitable divisions, even when there's no external authority enforcing fairness.
So how does EGT explain that?
Well, replicator dynamics models show that if individuals interact repeatedly, and if there are costs associated with being perceived as unfair, then strategies that involve more equitable divisions can actually become evolutionarily stable.
So it's not just about altruism or a sense of justice. It's about the long-term strategic advantages of being perceived as fair.
Exactly. By cooperating and sharing resources in a reasonably equitable way, individuals can build trust, avoid costly conflicts, and increase their chances of future interactions.
That makes sense. It's like a reputation system where being fair enhances your standing in the community and ultimately leads to better outcomes for everyone involved.
Precisely. And this is just one example of how EGT can shed light on the evolution of social norms and behaviors. By modeling the strategic interactions of individuals over time, we can start to understand how complex social phenomena, from cooperation to altruism to even morality itself, might have emerged.
This is all incredibly thought-provoking. It's like we're taking those abstract philosophical concepts and grounding them in a more concrete and dynamic framework.
That's one of the most exciting things about EGT. It provides a bridge between the world of ideas and the world of empirical observation.
It allows us to test our philosophical assumptions and to explore alternative explanations for the patterns we see in the world around us.
Exactly. And as we delve deeper into EGT, we'll encounter even more fascinating connections between this framework and the fundamental questions that philosophers have been grappling with for centuries.
Welcome back to our deep dive into evolutionary game theory. I feel like we've been on this incredible journey, exploring how this framework can help us understand how everything from cooperation to fairness evolved.
It is remarkable, isn't it, how EGT bridges that gap between individual behavior and these big patterns we see in society.
Exactly. In the last segment, we were talking about those different learning models and how they can shed light on the evolution of social norms. But I'm really curious to see how this all plays out in the real world. Can you give us some concrete examples of EGT in action?
Oh, absolutely. EGT has applications in a ton of fields, from economics and political science to biology and even computer science. Let's start with something that might seem a bit Well, mundane at first. Traffic.
Traffic, I gotta admit, I'm not immediately seeing the connection to game theory.
Think about it, though. Every time you get behind the wheel, you're essentially playing a strategic game with countless other drivers.
Okay, yeah, I can see that. We're all trying to get to our destinations as quickly as possible, but our choices affect each other.
Exactly. You have to decide, should I take the highway? It might be faster, but it's also prone to congestion. Or should I opt for the back roads? Could be slower, but maybe less crowded.
It's a classic dilemma. My best choice depends on what everyone else is doing.
Precisely. And EGT can help us model and understand how those individual decisions add up to the overall traffic patterns we see. It can help us explain why traffic jams happen and even suggest ways to, try to reduce them.
So EGT could actually help us solve real-world problems like
It
this.
has that potential, yeah. By understanding how drivers behave, we can design better traffic systems, implement smarter routing algorithms, even use incentives to encourage people to take less congested routes.
That's incredible. It sounds like EGT has a lot to offer when it comes to practical solutions.
And it's not just traffic. EGT is being used to study all kinds of social phenomena, everything from the spread of diseases to the evolution of language to how cooperation works in animal groups.
Speaking of animal groups, I've always been fascinated by how animals, even those that aren't closely related, can cooperate for mutual benefit, like those vampire bats you mentioned earlier, sharing their blood meals.
It is a remarkable example of cooperation, and EGT can help us understand how those kinds of behaviors might have evolved, even without kinship or direct reciprocity.
But how is that possible? Wouldn't it be more advantageous for an individual to just be selfish and hoard resources?
Who in a single interaction, maybe. But EGT models show that if individuals interact repeatedly, and there are ways to punish cheaters, then cooperation can actually become a stable strategy from an evolutionary standpoint.
So it's about the long-term benefits of cooperation outweighing the short-term gains of being selfish.
Exactly. And EGT lets us explore those dynamics to see how cooperation can emerge and stick around, even in environments that seem competitive.
This has been a really eye-opening exploration of evolutionary game theory. But I have to admit, I'm also starting to see some potential limitations or challenges with this framework. For example, it seems like EGT models often make simplifying assumptions about human behavior, like assuming that we're always rational or that we have perfect information.
You're right. Those are definitely important limitations to keep in mind. EGT models are simplifications of reality, and they can't capture all the nuances of human behavior, of course.
And even if we accept those simplifying assumptions, it seems like UGT models can sometimes lead to multiple possible outcomes.
That's true. EGT doesn't always give us clear-cut predictions. Sometimes different models can lead to different conclusions.
So how do we know which model to trust, or how to interpret the results?
Well, that's where things get even more interesting. It requires this careful back and forth between theoretical modeling, empirical observation, and philosophical reflection. We need to be aware of the assumptions we're making with each model, compare the predictions of different models, and be open to the possibility that there might be multiple valid explanations for what we're seeing.
So it's not about finding the answer, but about using EGT as a tool to explore the possibilities and to get a deeper understanding of the complex dynamics of social evolution.
Exactly. EGT is a powerful lens, but it's not a magic bullet. It requires critical thinking, careful interpretation, and, a healthy dose of skepticism.
This has been an amazing deep dive. We have explored the theoretical foundations of EGT, seen how it's used in all sorts of fields, and talked about its limitations. It's been a great conversation.
It is a field that's constantly evolving, and it's full of exciting possibilities for future research.
And it has some really profound implications for how we understand rationality, cooperation, and the very nature of human society.
Yeah.
It's given us a lot to think about.
So if you're intrigued by this intersection of evolution, game theory, and philosophy, I definitely encourage you to keep exploring this fascinating field. It's worth the deep dive.
And join us again next time on The Deep Dive, where we'll continue to explore the most thought-provoking ideas from across the intellectual landscape. Until then, keep questioning, keep exploring, and keep diving deep.